Hello, my name is Angelica Loshak, and today I'll be presenting CharliecLoud as a Kubernetes container runtime. This was a summer intern project in collaboration with another intern, London Bieliki, and now I'm excited to announce that I've been recently converted to a staff scientist at HPC for Lano. So first we'll go over Kubernetes for AI workflows, why Kubernetes hates CharliecLoud, and how we mitigate that, implementing the Container Runtime Interface, and does it work? Yes. So the motivation for this project was that our mentor Reed said that people doing AI workflows want Kubernetes, and solution, we implemented Kubernetes. So Kubernetes is important for AI workflows because it allows for containerization of AI applications for portability and consistency across HPC environments. It also allows for scalability and resource management, and for automation of machine learning pipelines and deployment. Kubernetes relies on various container runtimes such as Docker, Container, CRI, and these all implement the Container Runtime Interface, which is the main protocol for communication to the container runtime. And we want CharliecLoud to be on the list of container runtimes that Kubernetes can rely on. In order to do that, we need to understand the communication between Kubernetes and the container runtimes. Kubernetes implements the CRI client, and the container runtime implements the CRI server, which they communicate via a Unix socket. We want CharliecLoud to have this CRI server implemented so that it can communicate to Kubernetes. And we want CharliecLoud because HPC systems require a fully unprivileged container service that CharliecLoud provides. Also, luckily, Kubernetes allows users to specify the container runtime by changing the container runtime endpoint. So that's what we did here. We were able to specify our own CharliecLoud socket, and this is how we implemented it. The gRPC module was important to implement a long-lasting server on CharliecLoud. Here we create the gRPC server. Here we start the server, and now we can see that the server is running, and it is ready to connect to a Kubernetes client. We also need to understand the networking in Kubernetes. So a Kubernetes node consists of pods. They are on a network namespace, which communicates through a bridge. But CharliecLoud uses the host network namespace. So by default, this networking is not completely compatible. But by configuring the host network to true, we are able to put the pods on the host network namespace. There are also different approaches in container lifecycle management between Kubernetes and CharliecLoud. Kubernetes has more steps in its lifecycle, but CharliecLoud has a simple philosophy. So the lifecycle consists of running the container and then it being done. So we need to map these different functionalities between Kubernetes and CharliecLoud. This was our mappings to point out a few. The start container method maps to the chrun on the CharliecLoud side. The port forward is just a no-op, and pull image maps to image pull. So, for example, there were some methods that were easy to implement. They are just a one-to-one, such as the pull image method maps directly to image pull. However, other methods were not one-to-one. For example, create container and start container are both done by chrun in CharliecLoud. So we had to figure out how to do that. And the port forward is a no-op, and we just return a successful response because we don't need to forward the port in CharliecLoud because the containers use the host network namespace. So for example, Kubernetes will send a create container request. This consists of different fields, for example, container config, which has the image spec, which is the image that we want to pull. And in return, the function will respond with a create container response. And this consists of a container ID that the Kubernetes can use. So, for example, looking at this function, it is calling a sleep process, which runs the ch run with the sleep flag. And this sleep flag ignores any other user command, such as image name. And it calls this sleep forever function, which creates a long-running container process that just sleeps forever in order to keep the pod's namespace alive. And from there, we are able to join this sleep process using the sleeping process ID. And now that we join the namespace, we can run the user commands. In order to debug the methods, we use CRI-compatible, which is a tool for debugging CRI methods. It implements its own CRI client and can be used instead of Kubernetes to target the specific methods that we implemented and test that they work. So here is a demo of using CRI-compatible. We first create a sandbox config and a container config, and we can apply those configurations using CRI-compatible create. And the output of this is the container's ID. We use that container ID to start the container. Then we can list the containers using CRI-compatible PS. And we can see that the container is in a running state. So that means it is ready and we can execute commands on it. So here we are using CRI-compatible exec sync and specifying the command echo hello. And we see that it prints hello. So we see that it works. And now a demo with starting containers with the Kubernetes. First, we can check the node status by doing kubectl get nodes and see that it's in a ready status. So now we can create an application on the node and apply that those configurations using kubectl apply. And in the output, we can see that the pod was created. Next, we can check the pod status doing kubectl get pods. And we can see here our pod was created 30 seconds ago. And then we can do kubectl describe pods in order to get more information about that pod we just created. And along with other logs, we can see that it was created, it is pulling the image, and it started the container. So this is still a proof of concept and a work in progress. There's still more to implement, such as finish implementing other functions, such as attach and exec. Also, we want to support running the K3's rootless, because that will match with the CharliecLoud philosophy of being fully unprivileged. And we also want to improve the container lifecycle, such as handling memory exhaustion and the user and group ID configurations. But overall, it works. CharliecLoud and Kubernetes can create and start containers. They can track container metrics, run pods, respawn containers in pods. So like and subscribe for more code that works.
So you showed the initial diagram of the bridge network and sort of the local network within the node. So can you have containers that sort of talk across nodes? Like in a cluster with different, I guess, host machines in the cluster.
Your question is, can the containers talk with each other with Kubernetes?
So on a single machine, you have multiple containers with the local network.
Mm-hmm.
But can that network span multiple machines?
Mm-hmm. Yes, they can talk with each other. Yes.
So when you said that when you implemented the create container method with a sleep thing, so does that create one sleeping process per container that you create?
Yes.
Okay. And then do you have sometimes issues with sysadmins who then complain about ideal processes running without any usage on logging nodes or something like this?
Not sure how to run into that.
Thanks.
Any other questions for Angelica?
What would be involved in like implementing the own killer, or like what's the scene difficulties of that?
I guess like going into the configurations and managing the resources properly. Yeah, I don't see too many issues with that, just things we didn't get to.
So like there is a network mesh thing on, and is there anything like you have equivalent to the network mesh on like Kubernetes have the network thing that is like a network mesh, anything that is there.
Network mesh?
So a network mesh is like it's related to this question as well, like how they are talking to each other.
Okay, I'm not too familiar with that.
So I think like a network mask limits the spaces IP addresses you have. So some masks would say like only these 256 nodes or these 16 nodes or so on.
Is that managed in Kubernetes?
I haven't used Kubernetes enough to know about that.
I think that is one of the features.
Okay.
Okay, I guess I haven't ran into it much because my focus was on just the communication between CharliecLoud and Kubernetes. So I didn't get the chance to use Kubernetes more beyond that.
Any other questions?